binary search tree. Binary search tree. And so what has been discovered is that it's, in some sense, such a versatile data structure that you can do lots and lots of things with it, even though I'm not going to talk about all the possible functions. And many of the modern data structures that underlie, like, let's say, databases or the STL library are all built on binary search trees. So for example, I don't know if any of you have used SQL, like a database. If you've done database queries where you would say something like, okay, how many people, have a salary in this range and like live in this zip code and all these things. Like you have all these questions that are often asked of data, and then you want a quick answer. Often the underlying data structure is a binary search tree. So binary search trees, maybe pictorially, the way to think about it is we've seen linked lists. And so the idea of a linked list is that each node has like one successive node, one successor node. In a binary search tree, your nodes have two children. So your nodes are more complicated, usually referred to as left and right. So you have children, and often you also have a parent pointer. Right? So I guess raise your hand if you've seen a binary search tree before. Okay, so most of you have. So this is probably not news, but I'll just write this down. So sort of like the node class over here is, you'll have, so I'm just going to give it more generally. So you have some object that stores your data. You have some integer key. So all of the comparisons are done with respect to key. Usually you think of the key being unique for each object. The key could be stored as part of the data, but I'm just going to think of the key being separate. So there's a separate field called key. And then you have pointers to the left child, to the right child. These are these two pointers. And then often it's convenient to store a parent. So unlike a singly linked list, you can think it's kind of like a doubly linked list, right? In a doubly linked list, you can go backwards. And in a binary search tree, it will be convenient to have a parent pointer, which is to be able to go from a node to its parent. And if you look at the BST class, the binary search tree class, you have a special node that's called the root. So just like you have the head in a linked list, in a binary search tree, you have this node called the root. Right? So this is sort of the basic basics of a binary search tree. So especially when we start talking about binary search trees, and then we'll start talking about graphs after that, one uses a lot of more sort of discrete math and mathematical notation and definitions, and sort of a collection of terms regarding trees that I want to describe to you. And we'll be using these terms quite heavily. So I'm going to draw my nodes as circles rather than as boxes, because that's sort of the convention. You see, so you have a root, right? And then you have two children. So this would be the left child. This is the right child. And let me just, and then you have this. Okay. And so on and so forth. Maybe this doesn't exist. Okay. Okay, so you have two kinds of nodes. Well, there are many kinds of nodes in the tree, but certain things have certain names. So these nodes, this is called a leaf. So a leaf is no children. Any node without children is called a leaf. All other nodes are called internal nodes that are inside the tree. So anything that is not a leaf is an internal node. So an internal node has children. Now internal nodes are of two types. So this is one kind, whereas this is an internal node with two children. And that's an internal node with one child. Right? Does that make sense? So this is just a representation of the tree. And I'm going to first start with some definition, some notation regarding trees, because this will make it convenient to talk about things like insert, delete, and find, which are sort of, once we have the right terminology, it's actually it's easier to talk about these things. So the most common term that you will see, or one of the most common terms, is you'll see this notion of an ancestor. So I'll say W, so W is a node, is an ancestor of, let's say, X, if, so W and X are nodes. So for example, maybe that's W and that is X. So the definition actually uses recursion in some sense. It's an inductive definition, as we would call it mathematically. So think of the base case is if W is equals X. So what this means is a node is an ancestor of itself. Okay? And then the induction or the recursion, is W is a parent of an ancestor of X. Does that make sense? So a node is an ancestor. So a node is an ancestor of itself. So if W is a parent of an ancestor, then it's also an ancestor. So for example, the parent of X is therefore an ancestor, because it's the parent of X, which is an ancestor of itself, and hence the parent is an ancestor. And then the parent of the parent is an ancestor, so on and so forth. This is simply a more formal way of saying that if you take a node and you take its parent and parent of parent and parent of parent, so on and so forth, then you end up with ancestors. And those are the only nodes that are ancestors. So note that if you start from X and you follow the ancestors, you go up the tree to the root. That's basically just following the parent pointers. X and this node here are not ancestors. Does that make sense? So X and this node here are not ancestors. Maybe a thing that I should have said formally is if there is no child here, then technically that pointer is null. Right? That's the way that you would do it in the code. I'm not going to write the null pointers explicitly. Okay, but basically you would say that when the right child is null, then there is no child over there. Okay, so that's what an ancestor is. So the ancestors I'll say of X form a path from X to the root. So what that means is if you take X, the parent of X, and the parent of the parent of X, so on and so forth, you'll end up at the root. Right? So you're following these arrows backwards, and that takes you to the top. And so just like you have ancestor, you have a notion of a descendant. And we'll say X is a descendant of W if W is an ancestor of X, right? So these are just like the reverse of each other. So again, these are definitions. Like I have defined what an ancestor is through this process, then I define what a descendant is. Make sense? So far so good? Okay. Now we have a notion. So let's take this node W. And let me look at that part of the tree. This has a name. This is called the subtree rooted at W. Does that make sense? So I'm looking at all of these nodes here, everything here. Like starting from W and following the arrows downwards. That is referred to as the subtree rooted at W. Right? So there are these terms: ancestor, descendant, subtree. Subtree, internal node, leaf. Sorry, these 5 terms that I've defined here. Leaf, internal node, subtree, ancestor, descendant. Okay, so just to check that you're all following what I'm saying, I'm now going to ask you a question. So the question is, the subtree rooted at a node W involves all ancestors of W, all descendants of W, or both. Right? Both all ancestors and all descendants. Sorry. Okay, so this question makes sense. So the subtree rooted at W, at a node W, involves, is it involving all ancestors? Is it involving all descendants? Or is it involving both of them? I'll give you a minute to answer. So what is the answer? Yes, that's right. Most of you got it. It's blue. It's all descendants of W, right? So you start at W and you follow the arrows downwards. You mean you follow the children and the children of children, so on and so forth. Right? So that gives you all of the subtree rooted at W. Okay? So these definitions, this is sort of, it's a minor technical point, but I think it's worth emphasizing. These definitions have nothing to do with the fact that it's a binary search tree. This holds for a tree. This data structure is called a tree. Right? Right now, I haven't told you anything about what the keys look like. So a tree can be defined on any objects. It's just a mathematical object where you have a bunch of nodes and you have pointers between the nodes of this form. Right? A binary search tree is a special kind of tree where the keys have some property called the binary search property. Just like we had a heap invariant, we will have a binary search tree invariant. But I want to emphasize that the tree definition makes sense without talking about the keys themselves. Right? So the notion of an ancestor, a descendant, subtree, internal node have nothing to do about the keys. They only depend on the structure, which are the pointers. Is that distinction clear? Yes, no? So, so now let me tell you about the BST property or the invariant. Okay, so I'm going to use, again, I'm going to use more mathematical notation, so if something is confusing, please let me know. So I'll say for all nodes x, for all descendants y of x. So we have some node with some tree, we're looking at x, and then we're looking at some descendant y. Right? We follow the arrows downwards, you end up at a descendant. So for all nodes x, for all descendants y of x, if y is a descendant of x arrow left, right? So if y is going down the left side, then the key of y is going to be at most the key of x. And if y is a descendant of x arrow right, then y arrow key is greater than x arrow key. So I'll just say this because this often comes up and there's confusion. The equal to sign is only on one side. For now, for the discussion today and tomorrow, let's just assume that all the keys are distinct, right? And then that way you can just do less than and greater than. And when dealing with equal keys, you have to break ties one way or the other. So let's not worry about that now. But this property, okay, the reason why I wrote it this way is that the BST property gives what is called a constraint between the keys of ancestors and descendants. It doesn't talk about what happens between two nodes like these two. It doesn't say anything. There may be an implication that you can get, there might not, but it doesn't say anything. All it says is if you take two nodes, x and y, such that y is a descendant of x, then there's some condition on the keys. Now that condition depends on whether it's a descendant of the left side or a descendant of the right side. So another way of describing this pictorially is here's x. And again, this is only talking about the subtree rooted at x. Right? Remember, the subtree rooted at a node involves all descendants. So we are talking about the subtree rooted at x. And for every node in the subtree, there is a constraint. And this is the constraint that's given. So pictorially, this is described as if you look at the two children subtrees, this is less than the key, and this is more than the key. Right? Does that make sense? So this is again, like, because we were talking about heaps, the heap property is very different. This is maybe the more common one that you've seen. This is a constraint on the keys in the binary search tree. You can construct a tree where you don't satisfy this property, then it's not called a binary search tree. But if you have a binary search tree, then the keys must satisfy this property. Okay? So this is just like, remember, for a heap, we constructed that heap property and then find max became easy. So similarly, with this property, find is going to be easy. But then we have to figure out how to insert and delete maintaining this property. Because when you insert and delete, you might break this property and then you have to fix it. Although that's not going to happen, we'll carefully insert and delete so that this property is never broken. Does that make sense? So again, it's important to have this notion of there's an invariant. There is something that the data structure always guarantees you. That way, when you find, it's easy or it's fast. But then you have to ensure that when you update or change the data structure, you'll maintain that property. Yes? Okay. So if you've understood, which I hope you have, then I'm going to start writing some pseudocode for find. and I'm going to ask you to basically fill it in. Okay? All right. Any questions at this point? Okay. Yes? I'm sorry, say that again? Exactly. So the root has this property that the parent is null, exactly. And that's invariably where when you code up a binary search tree, your codes go wrong, because you forget to set that to be null, and then you end up with exceptions. Okay, just like in a linked list, I don't know, for those of you who've coded the linked list, hopefully all of you may have realized that, did you face null pointer problems? Yes, you face seg faults? Were the seg faults because of the head? Yes, no, sometimes, sometimes not. But often the head has to be dealt with separately, right? You have to do something different. So, but if you thought you faced seg faults with linked lists, just wait until you work with binary search trees. It's worse. It's much worse. And the easiest way to write code for a binary search tree is to make it recursive. It's just a lot easier than coming up with, and you'll see why. So let me write code to find. And so let's just say this is going to be of type node star. So it's going to return a node where I'm searching for an int that I call val. So I'm looking for a node whose key is val, right? So I'm always doing the comparisons with the key. Now, just like remember that when we did recursive find on a linked list, we had another argument, which is like the start node, right? And then we did recursion on that procedure. Similarly, for binary search trees, we'll have another start node. Okay, does that make sense? So there's going to be a start node here. So what this procedure does is it finds val in the subtree rooted at start. Right, so what it's saying is there's some binary search tree that is start, and the find is only running on the descendants of start. Yes? So val is a key. Yeah, you're looking for val is a key. So you're looking for a node whose key is val. Okay, so I'll write this out sort of more in English style pseudocode. So if start is null, that's the base case, return null. Or you could also say return start, but it's the same. If start arrow key is val, then you return start. Right? Okay. Now, if val is less than start arrow key, then what's the next line? What is the next line? Is it, do you recursively, so you're going to basically return, you're going to make a recursive call, return one of these. Are you going to return start arrow left, val, find start arrow right, val, or do you find start arrow parent of val, right? Which is, what's the next line that you have here? Right? What is the next line? Okay? Go and look at this property, look at this, and do it. Okay, so what is the answer? Yes, you're right. It is red. Although fewer of you have answered. So, any questions about this? This is a good time to ask because yes. It should be less than equal. Yeah, it should be less than equal. But I'm assuming that the keys are distinct. And technically, if it was equal, then you already found a node. If val was equal to start arrow key, you're already done in the second step. Yeah, you find the first one. Yeah. So actually, you don't need to put the equal to sign there. It is a. If you wanted to find all of them, then you would have to, maybe add this to a list and then do that. Yeah. Okay. Is this clear? Yes.
So like would the general order of like a pair be like the left one is like the least and then the parent is like a middle value and the right one is like the greatest?
Well, yes. So usually, if you look at this in order, it's everything in here, then the parent. So everything to the left, then the parent, then everything to the right. That's the overall ordering. And when we talk about tree traversals, you'll see that we'll use that to sort all the keys. But you see that if this is start, and if the val is less than start arrow key, then it has to lie in the left side. Again, it could lie somewhere else. It could lie somewhere over there. But the guarantees of this procedure are only that it finds in the subtree rooted at start. It doesn't find it if it's outside. Okay, that's sort of important to remember. This procedure only finds in the subtree rooted at start. Okay, so val is start arrow key. You would return find start arrow left val, and else you return find of start arrow right of val. And eventually, if you think, once you start thinking about it, you realize that's the efficiency of the binary search tree, because when you go down to the left side, you can ignore everything to the right side. So it's almost like what a binary search tree is doing is taking this idea of binary search and converting that to a data structure. Right? In binary search, you compare it the middle, and then you say, okay, like you ignore either the left half or the right half, and that's the same logic that happens here. That you get to ignore various portions of your data when you search, which, at some fundamental level is how you beat linear search. Is that for every query or everything that you look at, you want to be able to ignore certain portions of the data, and that's what's happening here. Okay, so this is find. And so if you think about insert, then the code to insert is actually very similar to the code to find. Because what you do is you try to find the node, you end up at a leaf, and then you just insert over there. So I'll write this down. By the way, I don't know if I'm going too slow. Am I going too slow? No. Okay, all right. Because if some of you have already seen this, then maybe this isn't new. But okay, so let's now do an insert using similar logic. So again, start. Now let's just, okay, so the way that I'm going to do this is, okay, I'm going to write something here and then to insert. So this is going to insert a node called to insert in the subtree rooted at start. Oh, so I forgot to say something. I should say something. So this is the procedure to find in the subtree rooted at start. What do you do if you want to find it in the whole tree? Yeah? You start at the root, right? So you would just do find root val. Just like in a linked list, you would do find head val, right? If you did it recursively. Okay, so as I said, I'm going to sort of skip over. Yes? Okay, good question. So why is this code starting at some intermediate node and not at the root? Yeah? Because you're doing it recursively. And so when you do the recursion, you're calling it on some other node here. Right? So if you were to do it iteratively using a while loop, then what you would have is you would have a while loop that says, while start not equal to null, you would have this where start keeps changing, or current. Does that make sense? But I guarantee you, when you're writing your binary search tree codes, if you write it recursively, it's a lot easier to manage. Right? Just conceptually, it becomes easy to think about. Okay? Right? Questions? Okay. So the way that I want to think about insert again is I have some nodes start here. I'm assuming that I've created a node called toInsert. So, I'm not going to write down the code for that, but assume that you call the constructor, you put your data, you put the key in that node, and now you need to attach this node to the tree. To the tree rooted at start. And again, the reason that we have this extra start is because eventually we'll call this recursive. It's a recursive function. Eventually we just start. Start will be the root. Okay? And so let me sort of let me write it this way, and then if there are any confusions, let me know. So I'm going to be again a little less careful with managing corner cases here, but so I'll say if toInsert arrow key. So this is the key that is in there, is less than equal to start arrow key. So if the key in here is less than the key of start, then I have to go to the left side, right? I have to insert somewhere over here. Does that make sense? I have to insert somewhere in the left subtree. So what is the base case here? Well, the base case is, okay, so you have this if condition. So I'll say this is 1. A is if start arrow left is null. Then you've discovered like an empty spot where you can now insert this key, insert this node. So then what we'll say is we'll do start arrow left is equal to toInsert, and then toInsert arrow parent is what? Start, right? So in this picture, what has happened is this was start. Maybe there was something over here, but that was null. So you can just put toInsert right there. And of course, you have to set the parent pointers. I'm not drawing the parent pointers because then my figures will be really messy. But again, yes? The children of this? So that's a good question. So I'm assuming that when I construct that node, all of its pointers are null. Its children and parent pointers are null. That would be in the constructor. Exactly. That would be in the constructor. Right. That would be in the constructor. Okay. So this is what happens if start arrow left is null. Else, just to make sure you're awake, what is the next line? Are you going to insert start to insert, are you going to insert start arrow left to insert, or do you insert start arrow right to insert? Okay, so I'll give you a minute. What is the next line of code? Okay, so what is the answer? Most of you see, yes, it is blue, that's right. So you would insert start arrow left to insert. So you see, hopefully, you would agree with me that the recursive way of writing it is quite clear. Right? It's really convenient to do it using recursion. And so I want you to always think about your binary search tree functions in terms of recursion. It's basically, it always boils down to you check something at the start node, and then either you recursively call to the left or you recursively call to the right. And that way you don't need to worry about while loops and conditions of that form. You have to just figure out the base case and then when to call to the left and when to call to the right. Right? That's basically what it all boils down to. Okay, so this is what happens if toInsert, the key in toInsert is less than equal to the key in start. And I put it less than equal to because when it's equal, I'm just pushing it to the left. Again, if you can assume that the keys are distinct, if that makes life easier. So this is what happens when insert the key is less than equal to. When it's greater than equal to, the logic is entirely the same, except you switch all the lefts to the rights. Right? And so again, you'll see this in binary search tree code, that you'll have one case and another case, and the only difference between the cases is just that left becomes right. Right? And you see that even over here, where you're doing the find, you're just switching the left to the right. And similarly, what happens here is if toInsert arrow key is greater than start arrow key, you do the same logic where you replace all the lefts with rights. Okay? So I'm not going to write all of that again, and I'll just say that if toInsert arrow key is greater than start arrow key, then switch left to right in the above code. Okay? Clear? Okay. I used to have slides for all of this. And then what happened is the first time I thought I had the slides, I showed the slides, and then someone asked a question, and I started writing to explain the answer. And then the feedback was, oh, the writing was way better than the slides. So I said, okay, I'll just write everything. Again, possibly because the speed at which I write is the speed at which you comprehend things. Whereas with slides, I just sort of flash them and you lose it. Yeah? Say it again? Good question. Okay, so yes, this only inserts at the leaves. But so the second part was, what if you need to insert somewhere in the middle? And my question is, why do you need to insert in the middle? So it turns out, or maybe I'll answer, you can always maintain the BST invariant by only inserting at the leaves. You never need to insert in the middle. Because Okay, so what you would believe me, hopefully, is that when you do this insert, the binary search tree property is maintained. And if the invariant is maintained, then you can do a find. And that's all that you care about. Does that make sense? No, you don't seem convinced. Yes? That's essentially one way of thinking about it. The point is that you'll always find a place to insert that is valid. Right? You'll always, so think of it as if you're looking for a node. Well, okay, so let me see if I say this correctly. Okay, yes, it won't be balanced. That we'll figure out. That's the next lecture. Yes, so balancing is a much more difficult thing. You're right that, yes, it won't be balanced. But even the ones that balance don't insert in the middle. They always insert at the leaves and then rearrange the tree in some way. Yeah?
Would it be possible to go left and then you have, if you go left, there could be a value in the right side of the tree that could be greater than the value of the inserted?
Yes, it can happen. So, okay, maybe I should draw an example here. So what could happen is, again, as usual, we want to insert 42. And so what could happen is that maybe this is 100, right? So you go down to the left, and then what you see over here might be 10. So then you would go down to the right. And then maybe what you see here is 40. So then you, again, go down to the right. But then what you see here is 50. So then you go down to the left. And that's null, and then you would insert 42 over here. Does that make sense? So you always will find an empty spot. It's just that you will keep traversing this tree in this way.
But wouldn't that make finding sometimes give you it would give you a answer, but wouldn't it not give all the answers?
If you want to find all the nodes that have a particular key, then that's a more complicated procedure. Let's assume for now that all keys are distinct. So if you assume that all keys are distinct, if you start at the root, you will always find the answer. Is that the point of confusion? Why do you always find the answer? Okay, so let's start. Look at the find procedure. The node lies okay, so technically, the mathematical proof of this is by induction, which is sort of the mathematical equivalent of recursion. But the way to think about it is, if the value exists, then it's obviously some descendant of the root node, right? If it's a descendant of the root node, it's either a descendant of the left node or a descendant of the right node, or it's at the root. Those are the only three possibilities. The node, if it exists, is either the start, is either the root, or it's a descendant of the left or a descendant of the right. And if it's a descendant of the left node, then its value is smaller. And so the recursive process will find it. And if it's more, then it's a descendant of the right node, and so then the right process will find it. Does that answer your question? Yeah. Sort of, kind of, yeah. Yeah. Yes. Exactly. It keeps going until it finds an empty spot and then inserts it there. Note that empty spot could mean, in this example, maybe there was some stuff that was already there. But the left child was null, so it just went and stuck it over there. So it's just going to keep, it's essentially, if you look at what it's doing, it's very similar to find. It's almost like it's just running the find procedure, but even when it's equal, it's just continuously moving until it gets to the base case and then goes and inserts over there. Because the base case is like it exited the tree, so when it exits the tree, it goes ahead and inserts there. Is that clear? Yes?
So the node 40, could that be larger than 100?
Could that be larger than 100? Good question. Could it be larger than 100? No, why not? Because it's a left descendant. It's a descendant of the left child. It doesn't matter, like if you go left and then you keep going right, you will still encounter things that are less than 100. Does that make sense? So in some sense, okay, so maybe this is a good thing to ask. So here's a node, right? That has 100. You went here, that has 10. Now let's look at all the values here. Okay? Which of these is true? Which is true for all nodes in T? So T denotes that subtree there. Is it key is greater than 10? Key is less than or equal to 100? Or is it both? So I'll give you a moment to think about it and answer. Which is true? Yeah, so what's the answer? What's the answer? Green, right? Both of these things are true, right? So all the values in T are sandwiched between 10 and 100. Does that explain better why it finds, right? Because once you go to the middle, you know that it's everything in this range. So if you actually think a little bit more carefully about it, what happens is, sorry, just a second, is that as it goes down the tree, there's a particular range of values that it's maintaining, and that range keeps reducing. So let's say from here, so right now, if you think about it, all the nodes here, okay, so are in the range 10 and 100. Once it goes down here, which of these is going to change? The 10 is going to change, right? Because at this point, it's going to be larger than whatever is over here. And then if it goes to the left, the 100 is going to change. So it's going to keep shrinking these until it finally reaches a leaf where the range is just, it's a single value. Does that make sense? So it's important to realize that the range always shrinks. It never, neither of the ends can go up or down. So somebody had a question in the back, yeah. I'm sorry, say that again? So I'm assuming that all the keys are distinct. I'm assuming all the keys are distinct, but if the keys were not distinct, then you could have any number of nodes in the tree. But you need to arrange them with the binary search tree property so that you can find when you need to. So I guess the key is to remember that the find, you've built the binary search tree to optimize find. And find is only going to work if this invariant is true. So it's almost like, okay, let's pop back, right? Think of it as, what is the problem with the linked list? Finding is hard, or it takes too long. So we'd like to do binary search, but we also want to insert and delete quickly. So okay, maybe I should have shown that table. If you remember the table of insert, delete, and find. So remember that a sorted array and unsorted array in linked list, they would always do one of the operations well and one of the operations poorly, or like two of them well and one of them poorly. What the binary search tree is trying to do is to try to do all of them well. To do all of them well, to get the find, it has to maintain the binary search tree property. So find becomes easy. But then it has to insert so that this property isn't affected. And that insertion is done in this way, right? Basically, it recreates the find and then goes ahead and inserts. Is that sort of clear? Yeah.
So if the first recursive call was started at the
Yes. Okay. So you're right that if you were to call this function from the middle without seeing what's at the parent, you would break the invariant. So you always call this function, I mean, so technically, if you were to do it sort of using object-oriented programming, you'd probably make this a private method and only expose the public method that calls at the root. Right? That way you could maintain the property. Yeah. Question or? Okay. Yes.
Wouldn't this be like, say you have a binary search tree that starts at like 1, and then it keeps going to the right, but it never goes to the left? Wouldn't that just be like as inefficient as like a
As a linked list, yes. You're getting ahead. Yes, you're right. So the thing is, the way that this insert is structured, you could end up with basically a linked list. And we'll go over that probably the next lecture. Okay. So far so good. So this is, so we have done find, and we've done insert, which are always the easier procedures. And so delete is now complicated. And so we need to figure out how to figure out delete. It's about an hour since we started. So let's take a break for 5 minutes, and then we'll do delete. Yeah.
Can you explain this again? I'm kind of confused. The property invariant, I got kind of lost here.
So All right, so let's now continue. Let's continue with the deletion procedure. So delete is complicated. We can just end here. Delete is complicated. Go and read it yourself. But no. So why is it complicated? Is because there are many cases. So, and this is again, like, I don't know, for like even if you think about linked lists, it's similar, right? Delete is kind of complicated because you could delete the head and then you have to worry about that. And so let me write, so instead of sort of like writing out pseudocode, what I'll do is I'll try and break up the cases and write a little bit of like sort of some pseudocode snippets for each. So I'm going to assume that you get a pointer to a node that needs to be deleted. Right? This is a pointer to the node that needs to be deleted. I'm assuming that you can, if you wanted to actually delete a particular value, like you would first search for it. You would find the node using the find procedure, and then that gives you the pointer to delete. Right? So that's the way you would usually structure this. So if you're trying to delete from a key, you would first find a node with that key. Once you get a pointer to that node, then you would call this function. Right? So this is really where all the action is happening. Okay, so case 0, which is the easiest case, is that toDelete is a leaf. So it's 0 children. Right? What that means is here's your node to delete. It's pretty easy. Right? So it's a child of some x. All you do is you reset pointers in x to be null. Does that make sense? So you just make this pointer null. Of course, you have to then fix the pointers of toDelete. You have to make its parent null. So you have to do some pointer changes. Even this, when you write the code, it's annoying because there are a bunch of cases. It depends on whether this node is the left child of x or the right child, and you have to set the pointers accordingly. Yeah?
So do we reset both pointers and then add the right child again, or do we just clear the left pointer?
For x, you would only clear the left child because there could be stuff over here. Right? So you have to be careful that you don't destroy the tree. This is exactly why you get lots of errors when you do a binary search tree. You have to be careful with the pointers, right? Because so when you want to delete this node, you only make that null, right? You don't want to change this pointer. And so you need to know, is toDelete a left child or a right child of the parent? So you have to go look at the parent, figure all of that stuff out. So it's a few lines of code to do that. And this was the easy case, right? So pay attention. So the built-in delete function would only free the memory. It wouldn't set the pointer of x to null, right? It wouldn't set that left pointer to null. Somebody, yes?
To do what you said just now about having to find whether we're the left child or the right child, we can just compare the key values?
You just compare the key values, yeah. So that's why we assume that the keys are distinct to make life easy. Yeah. Always in a binary search tree, the keys are usually unique. So if the keys were not unique, then you would like add a timestamp to it or something to make it all unique. And that way you can compare the nodes. Okay, so is that clear? Okay, so this is case 0, where toDelete is a leaf. Now, case 1 is toDelete has exactly one child. Okay, so there are multiple possible situations you have. There are actually 4 possible situations. So I'm shading the one that needs to be deleted. So this is toDelete. It could look like that. So here's x, y. look like that. X, Y. It could look like that. Okay? But you'll see that in each of these situations, what you can do is you can splice the node. What this means is you make Y a child of X appropriately. What this means is, in this case, you would just make Y a child of X. You could remove this in all of these cases. Now note that there is a distinction. Okay, so what is the difference between the cases on the left and the cases on the right? Like on splicing the node, what happens? You see? Yeah? So, right, so in the right-hand cases, okay, so somebody else had their hand up, so there's, yeah.
The parent is either having to point to the child on its right side or left side.
Exactly, so that's the distinction, right? In both of these cases, X's right child is going to become Y, and in both of these cases, X's left child is going to become Y. Right? And then you have to fix the parent pointers and all appropriately. But what's important to note is in both of these cases, as was said, the key of Y is larger. So you can always make it a child, a right child. So even if there is stuff over here, because of the BST property, everything over here is more than X arrow key. Right? All of this is more than X arrow key. And so you can do the deletion by resetting that way. So there are lots of pointers that need to be updated here, right? And so you have to do it a little carefully. You have to, and there are two cases. Even in this case one, there are two different cases. Even in the leaf, there are actually two different cases. But in this, there are two cases based on this, right? But again, this is all just a pointer manipulation. I think they're like maybe, I don't know. So you have to reset the parent pointer of Y, and you have to reset the child pointer of X. Does this picture make sense? Yes? So hopefully, I mean, again, I'll share my codes with you, so you'll see it done. But you'll see that, you know, it's just a few lines of pointer manipulation, which you have to do carefully. All right? Should I work out one of the cases? Yes? No? Raise your hand if it is yes. Okay, and raise your hand if it's no. Okay, fine, all right. All right, so let's work this case out. No, what the heck, you work it out. I'm going to give you a bunch of options, right? And you figure it out. So, all right. So, what is X? This is the parent of 2 delete. Okay, so what is Y? Yeah? It depends, right? So it depends on which of these cases we're in. So let's go ahead with this case. Okay, I'm working out this case here. So
Then it would be 2 delete left.
2 delete left. All right, so now there are 2 lines of code that need to be done. So what are the options for this? X arrow left is equal to Y. Y arrow left is equal to X, or X arrow right is equal to Y. Right? So we're looking at this case here. I've drawn that over there. Which of these is the correct line of code? You have a question? Yeah.
Are we doing this with the assumption that the one to delete is going to be a left child of x?
Yes, this case over here.
Okay.
Yeah, so I've already specified what x and y are. Yeah, this case. Yeah, so I'll give you a minute. I'm just drawing out the case over here so that there's a cleaner picture. Okay, so what happens? Yes, what is the answer? Right, so it's red. It's x arrow left equals y, because it's actually usually a bad thing to use y as a variable, because I'm going to ask you why is this happening and why is that happening, and it just becomes confusing, but it's y. So you see that I'm going to replace this tree with that. Right? That's the splicing operation. So x arrow left is equal to y, and y's parent is equal to x. Right? And so in this case, y becomes defined differently, but the fix is the same. And in these cases, so essentially these two lines will stay the same in all cases, right? Because you find the parent and you find and you reset the parent over here. But these two lines will change, and there are sort of, each line has two possibilities. So there's 2 times 2, there are 4 possibilities that cover the 4 different cases. Okay? And we're still doing the easy parts here, right? So now the painful one is the next case. So what is the case that's left? 2 children, exactly. And now it's not so clear how you would remove that node. So the painful one is when 2 delete has 2 children. And so I promise you, I'm not going to make you do this in the test, right? I'm going to give you the code to delete from a binary search tree. I don't think I've ever heard someone asking that like in an interview, because it's a lot of work. Okay, so here's the situation that we need to worry about. And this is to delete. So, yes? So it depends. So the way that I've coded this up is you don't free that memory, you just return that node itself, but you set all of its children and parent pointers to null. And then usually there's some other process outside that would delete and free that node. You could, again, depending on what you need to do, you could free the memory, or usually you delete because you want to do something with that number. I think, I don't know, now I don't remember. I think in my linked list code I've also done that, right? You can either delete a node or you can delete and free it, in which case you delete it and then you just free it from memory. Yeah. Okay, so now it's not clear how you would modify the tree to fix this, because for example, everything, okay, so I'm just, okay, so everything here is less than 2 delete arrow key. Everything over here is more than 2 delete arrow key. What about that? Is that more or less than 2 delete arrow key? Parent. Less, right? So this is also less than 2 delete arrow key. So this is less, this is less, this is more. Right? And it seems like, if you remove this node out, who do you actually set to be the right child of that node? Right? Yeah? Push what up?
Push the right side to where
But this is an entire tree. So this needs a parent now. Like this node needs a new parent. Who's going to become the new parent of this node? Is it some node in here? You could try to maybe find and then like do something, or yeah?
you have to like recursively move the subtree or root node each time up to the previous one, and then keep moving up until you get down to the bottom.
You yeah? You could take everything, put it into a hash map, and then like build everything back, right? This is usually the solution that you would give me. Can we just use a hash map to do this, right? So, yeah, it seems painful, right? That you would note that you cannot simply take this node and move it up, because if you move this node over here, now what happens to its children? There are 2 children already there, and then there's a third node here, and this node cannot end up with 3 children. And so it seems that you're going to have to do lots of restructuring. Or it turns out there's a clever fix where instead of trying to mess with the structure of the tree, you try to swap the contents of the tree and move it back to case 1. Okay, so I'm going to do this carefully. We do something that you'll hear a lot more like in maybe 102 and 103. We do something called a reduction, which is we convert case 2 to case 1 by a data swap. So what we'll do is we'll replace, or you can think of swap, the content of 2 delete. So by the content, I mean both the data and the key, right? With another node. Then delete the other node. Delete the other node using case 0 or case 1. So you have to find a node. We're going to find a node so that you can actually swap the content of that node with the node to delete in such a way that you don't mess with the binary search tree property. And then you go and delete that other node. And that other node will fall in cases 1 or 2, 0 or 1, which was easy. Does that make sense? So you kind of have to, so instead of trying to mess with the tree, it's easier to find some node whose data can go there. Now the question is, whose data can go there? Which key can go there? Yeah? The greatest node in the left subtree.
Whatever the parent is, if you were insert the node you want to delete in.
Right, okay. You could basically say that something like, if this was not there and I go ahead and try to insert, where would it get inserted? Find that node. Yes? Although it is easier to think about it in terms of, there is a very specific node. Yeah? Okay, why? Good. So let's look at that again. So we want to delete this node. So let's give this some names, okay? So this is X, right? I said I won't call things Y, so I'm going to call this W. I'll call this Z. So why can you, why for one of you who answered? So yeah, so why choose that node? Okay. So it might not be a leaf though, because you're just going right. It might have a left child in the end, but that's still okay. There's only one, exactly. Yes, case 1. Yes. W is larger than x and smaller than z. So let's maybe write down a few things over here. I'm not going to write the key. I'm not going to write arrow key because it's just painful. So what you know is that x is less than w, x is less than 2 delete, x is less than z, right? So x is less than everybody here. You know that w is less than 2 delete, and z is greater than 2 delete, right? So what you want to do is you want to find a key that kind of satisfies these conditions. That make sense? You want to find a number that satisfies these conditions. Indeed, if you find something, so I'll be more specific. So let me call this TL and TR. We need to find a key, okay? I'll refer to this key as K, such that all keys in TL are smaller than K, and all keys in TR are greater than K. Does this make sense? If I can find such a key K, then I can move that K to 2 delete, and it wouldn't break anything. Also, actually, I need to find a key that's more than x. Right? So if I can find a key which is greater than x, and which is kind of in between all the keys here and all the keys here, which is exactly what 2 delete is doing, right? The original key was in between the keys of TL and TR. So let me try to draw a picture here. I'm just drawing like on a number line. This is x. This is 2 delete. All the keys in TL are somewhere here, and all the keys in TR are somewhere there. Does this make sense? This picture makes sense, right? Because everything is more than x, but 2 delete is in the middle of TL and TR. What you want to do is you want to find another key that can take its position. And it makes sense that either use that one or use that one, and you still have that property. Right? Either use the maximum of TL or the minimum of TR. I don't get a good vibe. There's a lot of puzzlement in the air, right? Okay, you can see it or feel it or something. I don't know what it is. Yeah.
If you were to like generalize where those points would be like in the little corners of the triangles? Like moon-like corners? Is that what we're looking for?
Yes, because if you think about in a tree, where does the maximum lie? In any subtree, how do you get to the maximum? You just keep going right. If you want a minimum in a tree, you keep going left.
So then we just need to go, if it's on the right side, we just go left, 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 left. If it's on the left side, we go right, right, right.
And you can choose either. And the nice thing about that node is that node can only have one child, because you went all the way down to the right, so it doesn't have a right child.
Yeah.
Which means you can delete that using case 1. This is a bit clever, right? So this makes sense. So forget. You see that you need to find a key K such that all keys in TL are less than K and all keys in TR are greater than K. Let's assume that all the keys are distinct. So what is a key? I can give you 2 different keys that satisfy these properties. 2 different suggestions, which is the maximum of TL or the minimum of TR, which I've drawn here. And you can use either of those keys as a replacement for that. Yeah, kind of. It's the last 5 minutes, so Okay, so let me write this down, and you might have to go and stare at it. And the next lecture I can talk about this more. So I'll just say that let K be the rightmost node in the left subtree of 2delete. Right? This means that you just follow right pointers from 2delete arrow left. And note that 2delete arrow left is not null, because we are assuming that 2delete has two children. So neither of the children are null. So this node is what we'll do is we will simply copy the content of node X, or I should say swap the content of node K with 2delete. So just swap the content and then delete the node K using case 1 or case 0, depending on what happens here. So you went down here, you keep going right, that node is K. It might have a left child, it might not, but it definitely does not have a right child. That doesn't exist. And so deleting that node is easy. So what you do is you swap the contents of 2delete in K, and then you just delete the node K. Right? And the point is that K has either 0 or 1 child. Yes?
Since both the greatest of the left and the least of the right are valid, is there any other reason that it was arbitrarily chosen that he used the left?
It's just a convention that you could choose either of them. You could even, you could even try to optimize and say, well, I think that one of them is going to be quicker to find than the other, and then try to do that if you wanted. But it's usually, like, you could say which of these subtrees is smaller. If you stored that information, you could go and do that. But you could use either, and it would work. Right? Does that make sense? Yes? I'm sorry, say that again? No, actually, this doesn't affect anything. Like, all of this logic here is just saying whether X was here or X was there. But that doesn't affect